Good evening to all. A warm welcome to all for the second week tutorial session for the NPTEL course Convective Heat Transfer. My name is Ananthakrishnan. I am a Ph.D. student from Department of Mechanical Engineering, IIT Delhi. This session I do as a part of my PMRF TA duty. So in this week, we will see a few multiple choice questions and numerical type questions based on the second week lectures. It comprises of scaling analysis of momentum and energy equations, similarity solution, and integral solution for the momentum analysis. So we can move to the questions. See the question. This is the first question that is based on the flow over a flat plate, and that uses the Nusselt number equation and spin friction coefficient, and we need to find the solution. Consider the laminar boundary layer flow of an isothermal fluid. The fluid temperature is U infinity and T infinity, that is far away from the surface, over a flat plate, and the plate is kept at a constant temperature, isothermal wall at T0. At a certain distance x from the leading edge, the local skin friction coefficient is Cfx equal to 0.0066. What is the value of the local Nusselt number at the same location if the Prandtl number is 7? Local Nusselt number is given by this equation based on the Blazier solutions. And the skin friction coefficient is given as Cfx is equal to 0.664 Rex raised to -1/2. So this is given. So that is obtained from the Blazier solution that is taken from the text. So using these two equations, we need to find the value of the local Nusselt number if the Prandtl number equal to 7. Try to solve it, and meanwhile I'll also try to solve it after a couple of minutes. Okay, then I'll try to solve if you don't have an answer. So we need to calculate the value of the local Nusselt number at the same location if the Prandtl number is here equal to 7. So in this one, it is given that the local skin friction coefficient is given by this formula. So and the value is given as 0.006. So we can substitute it and straight away we will get the answer. It's equal to 0.664 into Reynolds number raised to -1/2. From this one, we can calculate the value of Reynolds number. So here we can say that Reynolds number is equal to the local value of the Reynolds number is equal to 1.1 into 10 power 4. So since it's a flow over a flat plate, this will be equal to the flow will be laminar since it's less than the transition Reynolds number of 5 into 10 power 5. So we can use the correlations for the Nusselt number. It's given that Nusselt number is equal to 0.332, Prandtl number is 1/3, Reynolds number is 1/6. So this is a correlation that we have obtained. If you have seen the lectures of professor, so this is the correlation for Nusselt number for Prandtl number greater than 1. So that implies the the velocity boundary layer, hydrodynamic boundary layer is greater than that of the thermal boundary layer. So the derivation of this involves the solution of the Blasius equations. It's a third order nonlinear differential equation, ordinary differential equation, and the solution involves shooting method. That was or we had to use some kind of numerical techniques to find the solution. So we can directly use this value. So Nusselt number is equal to 0.332 into Prandtl number raised to 1/3 into Reynolds number raised to 1/2. So for Prandtl number greater than 1, so we arrive at this equation. And then substituting the value of Reynolds number and Prandtl number, we'll get the 7 raised to 1/3, and Reynolds number is 1.01 into 10 power 4, the square root. So the value, it will be coming as 63.9. It is the value of a Nusselt number for a flow over flat plate at this Reynolds number. Now we can move into the next problem. It's a derivation question. Derive the we have to derive. So the problem says that we have to derive the expression for local Nusselt number along a flat wall with uniform heat fluxing using the integral method. Assume linear variation for velocity and temperature profiles, and the boundary layer thickness, hydrodynamic boundary layer thickness as 3.46 x Rex raised to -1/2. So this is a value of the boundary layer that we can get from the integral solution for a linear velocity profile. So we assume that this value is given, and we try to solve for the local Nusselt number for constant velocity and temperature, the linear velocity and temperature profiles. So you get the value of delta from the linear velocity profile. So it's already given. We need to calculate the heat transfer aspect of it. Try to solve it. Try to derive it basically. I'll try to solve it within a couple of minutes. Okay, I'll try to attempt this problem. So we have to derive the expression for local Nusselt number along a flat wall with uniform heat flux using the integral method. So the velocity boundary layer, hydrodynamic boundary layer is given as 3.46x into Rax raised to minus 1/2. And we could assume a linear velocity profile and a linear temperature profile in this case. So in this one, we'll try to draw the schematic. Next. So far away from the plate, the temperature will be T infinity, velocity will be U infinity, and assume this to be the thermal boundary layer, and the temperature it's a constant heat flux boundary condition, so we can uh, write as K double dash is equal to constant. The wall temperature keeps on varying with respect to X. In this program, we need to calculate the Nusselt number. So Nusselt number can be written as heat transfer coefficient into characteristic length divided by thermal conductivity. Equivalently, it could be written as the heat transfer coefficient can be written as, since it's a constant heat flux condition. So Q double dash divided by T surface temperature minus T far away from the wall. It's a Nusselt number at a local point multiplied by X divided by K. So this is the equation. For determining this one, we require the temperature profile and the value for calculating the Nusselt number. And represent it as 1. The integral equation for energy, integral energy equation, as mentioned by professor during his lectures, is given by dy dx of integral of 0 to y. Can assume this y to be some distance that is far away from the wall. This can be by 0 to y u into t infinity minus t into dy equal to alpha dou t by dou y at y is equal to 0. At y equal to 0. So this is obtained by integrating the energy equation and from 0 to y. The left hand side follows Leibniz theorem in order to consider the integral of a derivative into the form of a derivative of the integral and allay the constants. By applying the boundary conditions, we get this reduced form of the integral energy equation. So we can denote it by 2. And this is subject to the boundary condition of a constant wall heat flux is equal to minus of K into dou t by dou y at y is equal to 0 equal to constant. So in this case, we can, as given in the program, we can assume linear velocity profile u is equal to u infinity into u equal to u infinity into y divided by delta, assuming linear profiles. And similarly for the temperature, theta dimensionless temperature value T0 minus T divided by T0 minus T infinity is equal to y divided by delta T. We assume that the heat flux is incoming towards the fluid. That is a positive value. So this by equation 3 and this by equation 4. So two separate cases are there for the energy analysis. One is where the thermal boundary layer is very much bigger than or a higher than that of thermal boundary layer thickness is very much higher, very much bigger than that of the hydrodynamic boundary layer thickness. Second case, thermal boundary layer thickness is very much less than that of the hydrodynamic boundary layer thickness. So corresponding to this, when the thermal boundary layer is significantly lesser than that of the hydrodynamic boundary layer, we can say that when Prandtl number is very much greater than 1, that will be one case. And the second case will be Prandtl number will be very much less than 1 when the thermal boundary layer is is bigger than that of the hydrodynamic boundary layer. So the first case we will assume, case A, when the thermal boundary layer thickness is very much less than that of the hydrodynamic boundary layer, that is a case of Prandtl number very much greater than 1. So in that case, the energy equation represented by equation 2 will become, by making a few approximations, we have to determine the value of the U as well as we need to get the value of temperature profile as well. So the U will become, when delta T is very much less than delta U, so we can assume this is a thermal energy equation. So we need to get the value of the U for the energy equation. So correspondingly, for the boundary layer thickness, the scaling for this equation starts from 0 to y. We can assume this y to be some far distance, far away from the wall. In that case, this will be reducing into 0 to delta T, and from there this can be simplified into integration from 0 to y will become integration from 0 to delta T, and from delta T to delta, and then delta to y. The value of temperature. So the dimensionless temperature value theta will be equal to T0 minus T divided by T0 minus T infinity. So beyond the value of delta T, temperature will be equal to T infinity. So theta value will be equal to 1. And similarly, the value of U will be equal to U infinity y by delta. So the value of U in this range will be equal to U infinity into y by delta. So basically it means that in the energy equation, theta is equal to 1. When theta is equal to 1, the left hand side value U into T infinity minus T, when T will be equal to T infinity, will be equal to 0. So the energy equation left hand side value will be equal to 0. So it only stays from 0 to y will become 0 to delta T in this case. So within the delta T, the variation of U will be equal to U into U infinity y divided by delta T. So beyond that value, T will be equal to T infinity, and the energy equation reduces to 0 left hand side. And therefore the energy equation 1 becomes energy equation 2 becomes so the energy equation in this case it is equation 2. Equation 2 becomes equal to d by dx of 0 to delta t u infinity into y divided by delta t multiplied by t infinity minus t0, and we have to uh, within the boundary layer it will take the form of t infinity minus t0 multiplied by 1 minus of y by delta t. So we have to get the form of we have to get the value of t infinity minus t. The value of t will be the equation will be following a linear linear form. So we can write theta t infinity minus t divided by t0 minus t infinity is equal to y by delta. So what we have to determine is t infinity minus t, the value of t infinity minus t within the boundary layer, thermal boundary layer delta t. So we can write t will take the form of t infinity minus t will take the form of uh, t0 minus y by delta t of t0 minus t infinity. So that will be equal to t infinity minus uh, t0 plus y by delta t of t0 minus t infinity. So taking it out, it is equal to t infinity minus t0 minus of y by delta t of t infinity minus t0. Taking t infinity minus t0 out, will get in the form of 1 minus y by delta t. So in the original equation, it is in the form of t infinity minus t. So that will reduce to t infinity minus t0 into 1 minus delta t. So that is substituted in these equation. So this is can write it as I, and this is 2. So here it is substituting 2 and 1 in the original second equation. You'll get it reduced in this form. On the right hand side, we can write it in the form of alpha delta t divided by delta y divided by y equal to 0 can be written as linear differential. So t infinity minus t0 divided by delta t. So this is the new form of the energy equation for the case of Prandtl number very much greater than 1. And we need the in this case we know the value of beg your pardon, there was a slight correction. So this is not delta t, it is delta. So actually it will become equal to infinity beyond the value of y equal to delta. So from 0 to delta, the value will be equal to the range, the scale of the velocity will be scaled based on the hydrodynamic boundary layer thickness. So it will be u infinity into y by delta. So only these two are taken into consideration. So where the velocity will be scaled based on u infinity y by delta. It's a scale based on the delta. So the equation has got delta, delta t, and delta t. So in order to reduce it in the form of a delta t, you have to substitute the value of delta that is given in the problem. Therefore, substituting the value of delta equal to 3.46 x Rex raised to minus 1 by 2 in this equation, and then doing the integration. Okay. Divided by 3.46 x Rex raised to minus 1 by 2 T130 minus T0 into 1 minus 5 by delta T dy is equal to alpha T130 minus T0 divided by delta T. So in this case, the delta value is a function of x and Rex. That can be taken out of the uh, the integral, and can be both the sides can be integrated with respect to x after integrating with respect to delta t. So you get it's in the form of delta t divided by x is equal to, the final solution will be delta t divided by x is equal to 2.75 Prandtl number raised to minus 1 by 3 and a Reynolds number raised to minus 1 by 2. So that will be the form for the case of Prandtl number very much greater than one case. So the alternative case is when the Prandtl number is less than 1 and delta t is greater than delta for the case of when the thermal boundary layer is significantly higher than that of the velocity boundary layer. Here, in this case, the momentum diffusivity will be very much less than that of the thermal diffusivity. So in the first case, we have written only up to the delta t. Now we have to calculate the value of Nusselt number that we will calculate at the end by coupling both the cases. So in the case when the Prandtl number is very much less than 1, the hydrodynamic boundary layer will be very much less than that of the thermal boundary layer, delta. So in this case, the value of so beyond this value, the value of u will take the form of u infinity from this point onwards of the hydrodynamic boundary layer. That will be the free stream. So when we integrate the energy equation from 0 to y, the u will take the form of u infinity from delta onwards, and the value of temperature profile will vary linearly as per the problem. In that case, the value of temperature profile needs to be followed the same way as that of the previous example. So if I draw a temperature profile, it will remain a constant T infinity from this particular point onwards. It will be T0, T infinity, and this will be corresponding to delta T. So when the Prandtl number is very much less than 1, we could assume that delta T divided by delta is very much greater than 1, or delta by delta T is approximately equal to 0. So that is the most extreme case. In that case, we can get rid of the linear scaling of the velocity. So we can assume u is equal to u infinity. So that can simplify the problem significantly. And the second part, temperature profile, can be scaled just like the previous case. So the energy equation 2 will be equal to d by dx. In the previous case of Prandtl number greater than 1, we have to actually scale the velocity till the hydrodynamic boundary layer thickness. But here, since the thermal boundary layer thickness is high, we have to only take the value of u infinity, u equal to u infinity. You need not to take the linear profile in that case, in this particular case. So u will be equal to u infinity, and then temperature profile T infinity minus T0 into 1 minus y by delta T d by. So that will be equal to alpha into T infinity minus T0, just like the previous case, delta T. Here this is comparatively simpler because this is a function of everything else is a constant, and it's a function of only delta T, and integrating the value on the left and right, we can get delta T is equal to 2 alpha x divided by u infinity the whole raised to 1 by 2. So this is equation. We can denote this particular case as so this has equation 5 for Prandtl number greater than 1, and this has equation 6 for Prandtl number less than 1. So we know the value of delta 2 for both the cases. Now we can determine the value of Nusselt number. So determining the value of Nusselt number, determining Nu for Prandtl number less than 1 and Prandtl number greater than 1. For value of Prandtl number less than 1, in the present case, we can write delta T is equal to 2 alpha x divided by u infinity the whole power 1 by 2. The Nusselt number value, the given Nusselt number value will be equal to q double dash T0 x minus T infinity x divided by k. Sorry for the interruption. So for the case of Prandtl number less than 1, so we can write Nusselt number is equal to the following the same formula, q double dash divided by T0 minus T infinity, T0 of x minus T infinity of x by k. This whole term q double dash divided by T0 x minus T infinity divided by k can be written in the form of delta T. So basically that means that q double dash is same as that of k T0 minus T infinity divided by delta T. So taking delta T on the other side, we can write this will take the form of x divided by delta T. So substituting for Prandtl number less than 1, substituting the value of delta T, it will become x divided by 2 alpha x divided by u infinity the whole power 1 by 2. So making some rearrangements, so you can write x divided by 2 alpha divided by u infinity multiplying and dividing by the momentum diffusivity, we get in the form of this. We know that nu by alpha is equal to Prandtl number. So this corresponding term will be equal to 1 by Prandtl number, which goes on to the top will become equal to Prandtl number. So we can write that term outside. So it will be Prandtl number raised to 1 by 2, and clubbing the remaining terms together. So it will be 1 by root 2 into root of x u infinity divided by u. That is basically the Reynolds number term. So 1 by root 2 into Reynolds number raised to 1 by 2 into Prandtl number raised to 1 by 2 equal to 0.707. Reynolds number raised to 1 by 2, Prandtl number raised to 1 by 2. That will be the value of Nusselt number for Prandtl number very much less than 1. The other case which we have seen first, when the Prandtl number is very much greater than 1, we got the value of delta t by x. So we know that Nusselt number is equal to x by delta t. We know the value of delta t divided by x. So substituting the value, it will be inverse of this one. So 1 by 2.75. The Prandtl number raised to 1 by 3 and Reynolds number raised to 1 by 2 is equal to 1 by 2.75. Prandtl number raised to 1 by 3, Reynolds number raised to 1 by 2. So that will be the value of a Nusselt number for Prandtl number greater than 1 case. So this solves the problem. Basically, in this case, it's a case of an integral solution where we assume velocity, where it's given the problem that we could assume velocity profile and the temperature profile to be linear. The value of the boundary layer thickness, where hydrodynamic boundary layer thickness for linear velocity profile is also given in the problem as 3.46 into x raised to Rex raised to minus 1 by 2. So the question says how we can determine the value of the Nusselt number equations for this linear velocity profile. So as in with every other thermal boundary layer problem, thermal boundary layer can be very much bigger than or very much lesser than that of smaller than that of the hydrodynamic boundary layer. So that corresponds to Prandtl number greater than 1 when the velocity boundary layer, hydrodynamic boundary layer will be significantly high, or when Prandtl number very much less than 1, that is hydrodynamic boundary layer very much smaller than that of the thermal boundary layer. So we take both the cases, and for different cases, we calculate the value of the delta. We calculate the value of the velocity profile. In certain cases, we have to, when the delta is very much greater than delta t, we can't assume a velocity profile as such. The velocity profile within the delta t or the thermal boundary layer can take a linear form with respect to the boundary layer, with respect to the free stream as well as the wall velocity, that is 0. Similarly, the temperature scale that when scaled from 0 to delta t follows a linear scale, and we can consider that from the linear equation. This is for Prandtl number very much greater than 1 case, and for integrating the left hand side and right hand side, we'll get the value of the boundary layer thickness. And the Nusselt number is an inverse of, in this particular case, inverse of delta t divided by x, and we can get it straight away. And the second case is when the Prandtl number is very much less than 1. Here, it's very much simple. For this case, we can say that since we are scaling it from 0 to the thermal boundary layer thickness, we can assume that the velocity boundary layer thickness is very much less than 1 when the Prandtl number is very much less than 1. Velocity boundary layer thickness is very much small compared to the other thermal boundary layer. So throughout the thermal boundary layer, we could assume the velocity to be equal to the free stream velocity. And that simplifies the problem significantly. And the temperature scale or scale follows a linear scale as of the previous part of the problem. So from solving these, we can integrate and get the value of delta t in the form of this. So the Nusselt number will be inverse of this x, delta t by x, and we can substitute the value for both the cases and get the Nusselt number value for both the cases. So in the case of Prandtl number less than 1, you'll get it in the form of this one. Both of their powers will be raised to 1 by 2, Reynolds and Prandtl number. But in the case of Nusselt number, in the case of Prandtl number very much greater than 1, it will take in the form of this. That's also second problem. Now we can move to the next problem. It's a general problem. Look into the problem and try to solve it. I'll also try to solve it in a couple of minutes. So look into the problem. What are the global boundary conditions for flow over a flat plate? So this is a normal case. For an isothermal wall, what will be the boundary conditions? For the case, take the case of a wall at a temperature of TW and the free stream at a temperature of T infinity. How are we going to write the boundary conditions? So basically the first case at T infinity, here it will be T infinity and T0. Can assume so T0 at y is equal to 0 and T infinity at y equal to delta T. These two are a given. That's a common for all the four cases. Now what about the other two? So the first one is at y is equal to so how will we represent the value of the temperature gradient far away from the wall at y equal to delta T? How will uh, the value of the temperature gradient with respect to y be? Will it be 0 or will it be a constant value? So as far away from the wall, at thermal boundary layer thickness, we could say that the temperature variation drops. So it will be almost equal to T infinity at this point. So we could write that at y equal to delta T, dou T by dou y is equal to 0. So that will form the third boundary layer, the third boundary condition. So what will be the fourth boundary condition? So the fourth boundary condition is slightly tricky. So we have to determine it from the energy equation. So energy equation says that dou square T divided by dou y is equal to alpha dou T by sorry. By alpha. U dou T by dou x plus V dou T by dou y is equal to alpha dou square T divided by dou y squared. So this is the boundary condition. This is the energy equation. So how will we determine the value of dou square t divided by dou y squared at y is equal to 0? So basically at y is equal to 0, if you assume a non-permeable surface, we can say that v is equal to 0. And we can say that u is equal to, since no slip condition is there, we can assume u is equal to 0 for non-slip case. Therefore, the left-hand side will be equal to 0. And for both the cases, that implies dou square t divided by dou y square equal to 0 at y is equal to 0. So that will be the fourth boundary condition. So the correct option is at y is equal to 0, t is equal to t whole, y is equal to delta t is equal to t infinity, and y is equal to delta t, dou t by dou y is equal to 0, and y is equal to 0, dou square t divided by dou y square is equal to 0. So in that case, let us look into the other options. At y is equal to 0, dou t by dou y is equal to 0. That is wrong. There will be similar gradient. Tw minus t infinity divided by delta t, that is assuming a linear profile. At dou t by dou, that is not a boundary condition that happens throughout. And then dou square t divided by dou y squared is equal to 0 at delta t, y equal to delta t. That is wrong, because if you put the value of delta t is equal to y at y equal to delta t, so the second term will be equal to 0. What about the first term? U is equal to u into dou t by dou x is equal to alpha dou square t divided by dou y squared. So in that case, u will not be equal to 0, and dou t by dou x will also be not equal to 0. It can predict the variation of the temperature in the x direction at that particular point. Therefore, the value of the value of the boundary condition at y is equal to that is only feasible is at y is equal to 0, dou square t divided by dou square t divided by dou y squared is equal to 0, because that is derived from the energy equation, assuming the other boundary conditions. So the option A is a correct one. Now we can move to the next problem. This is a theoretical problem. We have to estimate the value of the pressure gradient for a flow or a flat plate using scaling analysis. So pressure gradient can be there for both the directions x and y. So how will we analyze the pressure gradients using the scaling analysis, especially for a flow or a flat plate? Try to solve it. I'll also try to solve it within a couple of minutes. So the given question says we have to estimate the value of pressure gradient from scaling analysis for flow over plate. So we can write it in the form of, we can write the momentum equations. So the momentum equations in the x direction will be x dou u by dou x plus y dou u by dou y. I beg your pardon. U dou u by dou x plus v dou u by dou y is equal to minus of 1 by rho dou p by dou x plus mu into dou square u divided by dou x square plus dou square u divided by dou y square. Similarly, in the y direction, it will be u dou v by dou x plus v dou v by dou y is equal to minus of 1 by rho dou p by dou y plus mu dou square v by dou x square plus dou square v divided by dou y square. And the continuity equation will be equal to dou u by dou x plus v plus dou v by dou y is equal to 0. So apply scaling analysis for a flow or a flat plate. So this is delta and this is L. So in this direction, the scale will be L, and in the y direction, the scale will be delta. So you can write, and far away from the wall, it will be u infinity free stream velocity, and we do not know the scale of v. So from this, we can assume that u infinity divided by L plus u infinity by L should be of the order of magnitude of that of v divided by delta. So if so in this case, we assume that the boundary layer is slender. That means that delta slender boundary layer, that is delta is very much less than that of L. So in that case, we can write, we cannot neglect both of the terms on the inertia side. So u infinity by L will be of the order of v by L. Since L is very much greater than that of delta, we can say that v will be very much less than that of u infinity. So we can neglect both the terms. So we can write v as u infinity by L into delta. But the one thing what we could write from this analysis is that since delta is less than, very much less than L, so in this particular term, this can be scaled with respect to L, and this can be scaled with respect to L. So on the bottom, it should be 1 by L square. That is a very small quantity, so that we can reduce it to 0. So slenderness criterion. Similarly, on the y side, since x is quite large, we can put is equal to 0, so, based on the slenderness criterion. But v can be scaled in the form of u infinity L divided by delta. That is the first part of it. But still, we do not know what will be the scale of the pressure, scaling of the pressure. So we know on the left hand side, u dou u by dou x V dou u by dou y in the experimental equation minus of dou p by dou x 1 by rho, and here it will be nu dou squared u divided by dou y squared. And this is of the form u infinity into dou u by dou x will take the form u infinity by L. Similarly, this V takes the form u infinity by L into delta into u infinity divided by y takes the form of delta. So basically, it will also reduce to u infinity square divided by L, u infinity square divided by L. So the scaling of minus 1 by rho dou p by dou x will also follow the same trend. On the y side, it will be u dou v by dou x plus v dou v by dou y. No, y and x minus of 1 by rho dou p by dou y and nu dou squared v divided by dou y squared. Here it will take the form u infinity, v will take the form u infinity delta divided by L divided by L. So this term also will follow the same scaling method. So it will be u infinity to delta by L, u infinity delta divided by L divided by y will follow the delta. So this basically it will become u infinity squared delta divided by L. And similarly, we'll get it in the form of u infinity squared delta divided by L squared. L squared. So we from this we can get the scale of minus 1 by rho dou p by dou x. That will be same as that of this scale, and the scale of minus 1 by rho dou p by dou y will be the same scale as that of this one. So from the scaling analysis, we'll get a scale of it that doesn't give you the actual value, but you'll get an approximate value or the order of magnitude of each of these quantities. So we can get the value of the pressure gradient. Now what comes now comes the next part of it. We need to actually get the value of the gradients. So in that case, we can write we can actually use the total, we can write dP in terms of the pressure gradient in terms of pressure gradient in the x direction and the pressure gradient in the y direction. So we take the total derivative. So dP is equal to dou p by dou x, total derivative of the pressure is dou p by dou x into dx. We assume only two direction in this case, dou p by dou y into dy. We know the scale of, so take the value of dP by dx. So this is taking the value gradient with respect to x direction. So it will be dou p by dou x into dx. That will be equal to dou p by dou x plus dou p by dou y into dy by dx. So here dou p by dou x will be of the order of u infinity will be of the order of the last term. So the last term will be of the order of nu into, we can write it as u infinity divided by y is delta squared. So the last term will be of order of this one. Similarly, here it will be order of nu into v squared plus v divided by y of the order of delta squared. So v can be written as u infinity into delta divided by L. So from this we can write dou p by dou x will be of the order of dou p, So this rho goes to the right direction. So rho into mu will be rho into nu will be mu. So it will be of the order of mu into u infinity divided by delta squared from scale of x momentum. Similarly, dou p by dou y will be equal to and we can get it from the scaling analysis. Dou p by dou y will be equal to mu v can be written divided by delta squared. So basically only v comes into picture. So v will be equal to u infinity into delta divided by L. Therefore, if you take the ratio of both the terms, it will be dou p by dou y into dy is equal to dou p by divided by dou p by dou x into dx. So dou p by dou y can be scaled as v infinity delta divided by L. Divided by delta squared into mu. Similarly, dou p by dou x mu infinity infinity divided by delta squared. So this delta gets cancelled. Mu gets cancelled. This u infinity gets cancelled. So basically, it will become I think I missed something here. Yeah. So that will be equal to delta square divided by delta L into dy by dx. So dy by dx also you need to scale separately. So that is delta by L into delta, dy will be delta and dx will be L. So that will be, so dou p by dou x, dou p by dou y into dy divided by dou p by dou x into dx will be scaled as delta divided by L. So we will take this for a boundary layer theory to be valid, delta, the slenderness ratio should be considered. So that is delta is very much less than L. That is part of the boundary layer theory. So that means that dou p by dou y will be 0. Dou p by dou y will be can be approximated to be 0. Therefore, dou p by dou x will be equal to dp by dx. So that means that the pressure gradient can be represented in the form of pressure gradient in the flow direction rather than the vertical direction. So total pressure gradient will be across the flow direction. So the original equation will become the u momentum equation, x momentum equation will become u dou u by dou x plus v dou u by dou y equal to minus of rho dou p by dou x plus v dou square u divided by dou y square. Now comes the last portion. So from the x momentum equation, you can get the value of dou p by dou x. Then how will you get the how will you solve for the actual value of dou p by dou x? So this says that the pressure gradient in the x direction will be same in the boundary layer will be same as that of the pressure gradient, total pressure gradient will be same as that of the pressure gradient in the x direction. So taking the boundary layer into consideration, So in this case, we can assume. So dou P by dou X will be equal to the ordinary gradient of the pressure with respect to ordinary differential of the pressure with respect to the X direction. So coming into, and also we can say that dou P by dou Y is close to zero. That is, vertical pressure gradient will be equal to zero. So that means that the pressure gradient in this vertical direction will be equal to zero. And since the external flow will be at a constant pressure in this vertical direction, we can assume that dou P by dou X will be the pressure difference within the flow in the X direction will be same as that of the pressure difference across the flow direction outside the stream as well. So we can write, since dou P by dou Y is equal to zero, just across the boundary layer, we could see that dou P by dou X in the free stream will be same as that of dou P by dou X away from the wall, but within the boundary layer. So we can write dou P by dou X, dP by dx within the boundary layer will be same as that of dP infinity divided by dx. So that solves part of the problem where we'll get the pressure gradient dP by dx, dP infinity by ds. So the next part comes application of this pressure gradient for the flow over the flat plate. So flow over the flat plate, the X momentum equation will be and in the free stream, we can write u dou u by dou X plus v dou u by dou Y is equal to minus of 1 by rho dou P infinity divided by dou X plus mu dou square u divided by dou Y squared plus dou square u divided by dou X squared. So since this is free stream far away from the wall, the inertial forces will be very much greater than that of the viscous forces. So these terms will be equal to zero. So here in this region, Euler's equation is valid for the inviscid flow, or where the viscous forces are neglected. So that means that dou P infinity by dou X by rho will be scaled according to u dou u by dou X. That is a variation of u in the X direction. So in this case, the total u will be u equal to u infinity throughout the free stream. That means that dou u by dou X equal to zero. So this term will be equal to zero. That means that dou P infinity by dou X dou P infinity by dou X equal to zero. Since dou P by dou X within the boundary layer equal to dou P infinity divided by dou X, and since this term equal to zero for only the flow over flat plate, for this particular subsection of the real flow or external flow over the surface, we can say that dou P by dou X for the boundary layer will be equal to zero. Therefore, the X momentum equation reduces to u dou u by dou X plus v dou u by dou Y is equal to nu dou squared u divided by dou Y squared. So that will be the reduced form of the X momentum equation, and dou P by dou X within the boundary layer will be equal to zero. So this is how we without considering any mathematical values or without considering any numerical value of these terms, just based on the scaling analysis, we can reduce the pressure gradients. And we can eliminate them for this particular case of flow over the flat plate by taking into consideration both the X and Y momentum equations as well as the Euler's equation for the flow for flow over a flat plate without any viscosity. So in that case, we can assume that the inertia term will be matchable with that of the pressure term outside the boundary layer. But since the pressure gradient will be zero, since everywhere it is free stream velocity of u infinity, you can assume the dou p by dou x equal to 0, and that will be traced back within the boundary layer as well. We can say that dou p by dou x will be same as that of dp by dx. And since dp by dy is equal to 0 just across the boundary layer, we can say that the same pressure gradient, the same pressure will be experienced at the exact position just besides the boundary layer on both the directions, outside the boundary layer as well as inside the boundary layer. And thereby we can say that dou p by dou y will be equal to 0. Therefore, the pressure at this particular point will be same as that of somewhere within the boundary layer as well. Now, since we know that dou p by these two pressures are same, and some at different points these two pressures are same, that means that the pressure gradient across these 2 points dou p by dou x will be same as that of the pressure gradient outside the boundary layer. And since from the Euler's equation, since we get dou p by dou x equal to 0, that can be traced back, and the pressure gradient within the boundary layer for a flat plate will be equal to 0, and the momentum equation reduces to only the inertial terms, two inertial terms and one viscous terms within the boundary layer. That completes this derivation, and we can move into the final problem of today's session. This is an integral solution for the boundary layer or a flat plate. Assume a quadratic velocity profile, and we have to find the boundary layer thickness and skin friction coefficient. It's a quadratic velocity profile. We need to find the boundary layer thickness and skin friction coefficient in this case. This considers only the momentum side of the integral equation. We need to use a quadratic velocity profile and solve it. I'll give you a minute and you can go through, and I'll also try to solve it. So did you try to attempt the problem? If not, I'll solve it. So, we have to consider the integral solution. We have to determine the integral solution for the boundary layer or a flat plate. We need to assume a quadratic velocity profile. And just like the first case, we have to, just like the first question, we have to determine the boundary layer thickness and skin friction coefficient. So this is an integral solution, and we have an integral equation, and we substitute the value of these. So we substitute the value of these quadratic velocity profile in the integral equation. So for that, first we need to write what is the integral velocity integral solution for the momentum equation. So the integral equation of the x momentum takes a form d by dx of u infinity squared delta equal to mu into dou u by dou y at y is equal to 0. So if you know the value of u, we can get the this is the momentum thickness. So delta 2 is the momentum thickness. So if you know the value of u, we can substitute it in this equation and get the value of boundary layer thickness and skin friction coefficient. So d by dx of u infinity squared into is equal to y is equal to 0. So this delta 2 can be written as integral of 0 to y u by u infinity of 1 by u infinity t by. So if you know the value of u, you substitute that here and get the value of the momentum thickness, then back substitute in the x momentum equation, and then we can get the value of delta from it. Delta 2 is the momentum thickness, and delta is the boundary layer thickness. So in this question, it is asked that we have to consider a quadratic velocity profile. So the quadratic velocity profile can be written as u is equal to a plus b by plus c y squared. And we assume some boundary conditions and get the value of the constant a, b, c. So the main boundary conditions, it has got three constants and we require three boundary conditions. So at y is equal to 0, no slip condition, we can say u is equal to 0. That is first boundary condition. Similarly, at y is equal to delta, we can say that u is equal to u infinity, that is free stream velocity. Similarly, at y is equal to delta, we can write dou u by dou y is equal to 0. Change in the velocity at the boundary layer thickness is equal to 0. Using these three equations, we can calculate the value of A, B, and C. So applying the boundary condition first, that implies that y is equal to 0, u equal to 0, that is equal to 0 is equal to A is equal to 0. Then apply, that implies u is equal to by plus cy squared. Applying the second boundary condition, applying the third boundary condition, that at y is equal to, I beg your pardon, applying the second boundary condition to the original value of u to 2 at y is equal to 0, u equal to 0. That implies 0 at y is equal to delta, u is equal to 0, u equal to u infinity. That gives u infinity equal to b delta plus c delta square. That is 5. Now boundary condition 3, at y equal to delta, dou u by dou y equal to 0, u will be taking this form. So that is 0 is equal to b plus 2c delta. Therefore, b is equal to minus of 2c delta. That is equation 6. Equation 5 gives u infinity is equal to b delta plus c delta square. Therefore, substituting b in terms of minus 2c delta, therefore we can get minus of 2c delta plus c delta square. I beg your pardon, minus 2c delta square, that is equal to minus c delta square. Therefore, we can write c is equal to minus of u infinity divided by delta square. That is equation 7. Therefore, b is equal to minus of 2c delta divided by 2u infinity divided by delta. So that will be the value of b. Substituting this in the u, we'll get 2u infinity divided by delta y minus u infinity divided by delta squared y. Therefore, we can write, we can just take u infinity to the other side and try to simplify the terms. It will be u by u infinity is equal to 2u by u y by delta minus of y by delta the whole square. This gives the third equation and the velocity profile of the quadratic in terms of quadratic terms. Now, since we have the velocity profile, we substitute this in the momentum thickness of delta 2 and get the value of delta 2 and substitute in this first equation of the integral momentum equation. So delta 2 will become therefore delta 2 will become equal to 0 to delta 2 into y by delta u by u infinity. So basically that means 2y by delta minus y by delta the whole square, this whole term multiplied by 1 minus of u by u infinity. So 2 into y by delta plus y by delta the whole square into dy. We substitute, we multiply the terms internally. Then we'll get 2y by delta minus 5 by y by delta the whole square plus 4 y by delta the whole cube and y by delta the whole raised to 4. This is by multiplying and simplifying the terms. So that will be, and then integrating it from 0 to delta, we get y by delta minus 5 by 3 y cube by delta squared plus y raised to 4 divided by delta cube minus y raised to 5 divided by 5 delta raised to 4 from 0 to delta. And just opening and substituting the upper and lower limits and reducing, we get 5 by 3 delta plus delta minus delta 5. So that will be equal to 2 by 15 delta. That will be equation 4. Now substitute equation 4 in the integral momentum equation. We'll get d by dx of u infinity square of delta t value, delta 2 value, that is delta momentum thickness value 2 by 15 delta is equal to nu dou u by dou y at y is equal to 0. Dou u by dou y at y is equal to 0 can be written as, we got the value of dou u by dou y at y is equal to 0. We just differentiate the u and put y is equal to 0. So only the 2 u by u infinity minus of only 2 u by u infinity by dou delta remains in that equation. So that will be 2 u infinity by delta, differentiating the velocity profile at y is equal to 0. Therefore, we will get take the constants outside, 2 by 15 delta 2 by 15 of u infinity squared d by dx of delta taking this delta on the left hand side and this u infinity here, 2 nu, 2 gets cancelled, u infinity square term gets cancelled, so it will be delta u infinity d delta by dx divided by 15 is equal to nu. Making some changes, I can write, we can take the delta inside, you multiply both numerator and denominator. So q delta d delta is a differential of d delta squared. D delta squared by dx is equal to 30 nu. Therefore, d delta squared divided by dx is equal to 30 nu divided by u infinity, and integrating both the sides with respect to x, we'll get delta squared is equal to 30 nu u infinity x. Therefore, delta is equal to root of 30 nu x divided by u infinity, that is equal to Reynolds number raised to take x on numerator and denominator, and this becomes delta by x is equal to root of 30 into Reynolds number at x raised to minus 1 by 2. So we'll get the profile for delta x. Delta x is equal to delta x divided by x is equal to 5.48 into Reynolds number at x raised to minus 1 by 2. So this is the velocity profile for a quadrant. This is the hydrodynamic boundary layer thickness with respect to a quadratic velocity profile. Now the second part of the problem, we have to determine the skin friction coefficient. The skin friction coefficient CFX is equal to the wall thickness, the shear stress of the wall divided by half into rho u infinity squared. So shear stress at the wall is equal to my nu dou u by dou y at y is equal to 0 half rho u infinity square. So this you can directly get from the velocity profile nu into dou u by dou y at y is equal to 0. We have already determined 2 by delta of u infinity divided by half rho u infinity square. Reducing the equation, you'll get 4 mu divided by rho u infinity. So it is dependent upon u infinity. That's why you require the value of the boundary layer thickness. Therefore, Cfx is equal to 4 mu divided by rho u infinity delta. And delta will be equal to 1 by 5.48 Reynolds number raised to x raised to minus 1 by 2 on the top and x on the bottom. Therefore, Cfx by clubbing the terms of rho u infinity x and mu on that is equal to Reynolds number. So we'll get it as 4 by 5.48 divided by 4 by 5.48 multiplied by Reynolds number multiplied by Reynolds number raised to minus 1 by 2 divided by Reynolds number raised to Reynolds number raised to 1. So that will be 4 by 5.48 will be equal to 4.73 divided by Reynolds number multiplied by Reynolds number raised to minus 1 by 2. I beg your pardon, this is on the top. This is, if it goes to the top, it is plus. So Reynolds number divided by Reynolds number raised to 1 by 2, that is equal to Reynolds number raised to 1 by 2. Therefore, Cfx is equal to 0.73 into Rex raised to 1 by 2. So that is the value of the skin friction coefficient with respect to Rex Reynolds number. So if you compare it with the Blacher solution, the value will be slightly off. Blacher solution is the accurate solution that can be obtained from the shooting method or from the similarity solution. And from the it's a non-linear third order differential equation that has to be solved numerically or using shooting method. And you'll get the value of skin friction coefficient as 0.664 Rex raised to 1 by 2 in that case. So, and similarly for the boundary layer thickness, that value will be equal to 4.92 instead of 5.48 that constant. So this is actually the difference that this much difference you can encounter while assuming a velocity profile. The actual velocity profile might be somewhere different. So the accuracy can be improved if you use cubic velocity profile instead of quadratic velocity profile. But even then, the actual value will be slightly off. Though you can get the value of the skin friction coefficient quite same. It may not be applicable for the case of the boundary layer thickness. So the boundary layer thickness, the constant will be 4.92, somewhere around 5 in the case of Blacher solution. But in the case of cubic profile, that will be 4.64. That completes the problem solving session for this week. So in this session, we have seen a few numerical type questions and one multiple choice question based on the scaling analysis, integral solution. So we didn't see a question on similarity solution because that is quite difficult actually. So that is a purely mathematical thing that we could arrive at this equation, but in order to solve the solution, we in order to get a solution, in order to solve that particular equation, we have to use numerical method or something similar, maybe shooting method to solve. That's why we couldn't see a problem of similarity solution. So, but we have seen enough questions on integral solution as well as the scaling analysis in this class. So in this so hope you understood the way it can be solved. If you have any doubts, you can post these problems, your problems on the forum that is available in the course website. So we'll meet next week with the tutorial session for the next week's lectures. And till that time, it's bye. Thank you.